In this video, we're going to look at the change of variable in multiple integrals. So we're going to compute the Jacobian of a given transformation. We're going to evaluate double integrals using a change of variables, and we're going to evaluate triple integrals using a change of variables. So first, we're going to do this warm-up. We're going to integrate this where x is greater than 1. So that means that we don't have to worry about the absolute value stuff. So the first thing we would have done in calculus 2 is we would have said, oh, this looks like a u sub. So we'd let u equal the natural log of x. Then du would equal 1 over x. So then this 1 over x dx gets replaced with a du, and this natural log of x gets replaced with u. And so I have the integration of 1 over u du, which of course integrates into the natural log of the absolute value of u plus c. So then this becomes the natural log, well, u was the natural log of x, and then plus c. And so we did this with u substitution. What we're going to be doing today is we're going to be using substitutions in 2 and in 3 variables. So the reason we always do substitution is because it usually makes the integration a little bit easier. Generally, we use this ability to make this integration easier. We're going to call it a transformation or mapping. So if we think about when we go from x, y into r theta, it would look like this, t being the transformation from x, y into r theta, where the map, the way I'm going to get from one to the other, would be r is equal to the square root of x squared plus y squared, and theta would equal the tangent inverse of y over x. Now, if we're going to go from r being our transformation of r and theta into x and y, then the quote map would be x would be r cosine theta and y would be r sine theta. A planar transformation t is a function that transforms one region in the plane into a different region into another plane by a change of variables. Now r and g are both subsets of R2. So we're going to start with a Cartesian UV plane, and I'm still going to be left with a Cartesian, now it's going to be an XY plane. And we're going to have some mapping that's going to change my UVs into X's and Y's. Typically, we assume that these functions are continuous on first partial derivatives, which means the partial derivative of g with respect to u, the partial derivative of g with respect to v, the partial derivative of h with respect to u, and the partial derivative of h with respect to v exists, and they're all continuous. Now, suppose t is some transformation from g into r, then the region g would be called the domain of the transformation t, and the region r is the range of the transformation of t, which is known as the image of g under the transformation t. So the transformation from the transformation t from g into r could be defined as t from u to v into xy is said to be one-to-one transformation if no two points map to the same image point. So in other words, there can be no value in my r that isn't mapped to g to begin with. And I can't have two values in g be mapped to the same value in r. So now we're going to try to determine with this example whether or not it's one-to-one. Well, okay. Suppose we have phi of u v. Well, this is going to go to u squared v. Now suppose my u is now a negative number, but it's also going to be mapped to negative u, the quantity squared v, which is the same thing as u squared v. And this is going to happen every time u is not equal to 0. So if I put in the point 1, 2, it's going to go to 1, 2. But if I put a negative 1, 2, it'll also go to 1, 2. So it's not one-to-one. Then I have to figure out what would be an appropriate value for one-to-one. So the domain, an appropriate domain for this to be one-to-one of my set u, v, could be any u greater than 0 or any u less than 0. So I'm going to say u greater than or equal to 0. So I could choose that, or I could have chose u is less than 0. One side or the other, u is less than or equal to 0. And then I don't have that problem about two values being mapped to more than one value, or two values being mapped to the same value in my image. Now I want to find the image of phi on the u and the y-axis. So let's start out what it would look like in terms of x and y. So if we are an x and y, then my phi of u and 0, that means I would be on the x-axis, similar to being on the x-axis, would be u squared comma 0. So that would tell me that the image on the u-axis is going to be the positive u-axis only. Now, if I do x, y, phi, and I'm going to look at what this would look like on the y-axis, but in the uv, so it would be 0 comma v. So this would be 0 squared comma v, which is just 0v. So this would just be the v-axis. And it would be all of it. Now similarly, this would be the positive x-axis, and this would be all of the y-axis. Now what I want to do is I want to find the image of phi on the rectangular region from -5 to 5 and from -5 to 5. So this is my u and this is my v. So basically u, the absolute value of u has to run between, the absolute value of u has to be less than 5. And similarly, the absolute value of v has to be less than or equal to 5. That is the same thing as going from -5 to 5 and -5 to 5. But we know that x is equal to u squared and y is equal to v. Then from this, we know that u is going to be plus and minus the square root of x, and v is going to equal y. That means the absolute value of the plus and minus the square root of x has to be less than or equal to 5. And since the smallest value that I could have for the square root for x would be 0, so I'd have the square root of x is less than or equal to, greater than 0, but less than or equal to 5, because I'm going to take the absolute value of it. Now if I square everything, I get 0 is less than or equal to x, which is less than or equal to 25. Now my y, since y is v, y, the absolute value of y, is less than or equal to 5, because that's what it was for v. And then -5 is less than or equal to y, which is less than or equal to 5. So then what I would have, so I'd have something that looks like this. I would go down from -5 to 5, all the way out from 0 to 25. And that's what the image would look like in the xy plane. We want to find the image of phi on the line segment joining from 0, 0 to 8, 8. Now we can see in this region from here to here that u is equal to v, that I have 0 equals 0 and 8 is equal to 8. But we also have the fact that u is equal to the square root of x. If u runs between 0 and 8, that means the square root of x is going to run between 0 and 8. That means x is going to run between 0 and 64. Now, if u is equal to v, but v is equal to y, that means y is equal to u, which is equal to the square root of x. So y is equal to the square root of x. Now what's happening is in my uv plane, I have this straight line. This is in the uv plane. When I map this to the xy plane, I'm going to end up with this, which is the square root. Y is equal to the square root of x. where I'm going to go for x is going to go between 0 and 64. So that's what's happening, is I am mapping my UV into the xy plane. UV are going to be equal to each other, and it's going to go from 0 to 8. But in the xy plane, it's going to be y is equal to the square root of x, and it's going to go from 0 to 64 for the x. In my next example, I'm going to use a nonlinear change of variables, and they're given these to me. I'm going to find x, so it is a function of u and v. I'm going to find y, so it's a function of u and v. So I'll start with the fact that since u is equal to x over y, then x is going to be u over y. Similarly, if I have v is equal to x over y, xy squared, then x is going to be equal to v over y squared. Since x's are equal, I have u over y is equal to v over y squared. Multiplying both sides by y squared, I'm going to get yu is equal to v. So y must be equal to v divided by u. So I have y, which is a function of u and v, which is equal to v divided by u. Now, since I have this here, to do my x is equal to u divided by y, which is going to be u divided by v divided by u, which is going to give me u squared divided by v. So then x as a function of u comma v is going to be u squared divided by v. And that's it. Now you're wondering, why am I doing all this? Well, it's actually going to make it a little bit easier, and we have been doing something similar to this when we've been doing our transformations from rectangular into polar, rectangular into cylindrical, rectangular into spherical, cylindrical into spherical. So we've been doing this the whole time. So now we're going to pick up something called a Jacobian. A Jacobian. Let the transformation t, uv, go into some function g of uv and some function h of uv, where x is equal to the g function and y is equal to the h function to be 1-to-1 and c 1, which means all the partial derivatives are continuous. So when you see this notation, c raised to the 1, that means that all the partial derivatives are continuous. I'm going to call this a transformation. We want to see how it transforms a small rectangular region S, delta U, by delta V units into the UV plane. So here's where we are. We do this transformation. This is the transformation. Since x and y are the position vectors of R of UV, and it is the image of the point UV, suppose I'm looking at an ordered pair where I have u sub naught, v sub naught, which will equal x sub naught, y naught. Then the line y is equal to v is equal to v naught maps the image of the curve to this function at the tangent, and we end up with this. The partial derivative of r with respect to u is a partial derivative of x with respect to u, the partial derivative of y with respect to u. Similarly, the vector r with derivative with respect to v is going to be, and these should be v's here. These should be v's here. Copy paste was not my friend. And it'll be the partial derivative of x with respect to v and the partial derivative of y with respect to v. Now, as we take the limit of this, we end up with the partial derivative, the delta u r with respect to u. So we take the limit of r sub v, we get the delta v sub r v. Now, the area then is going to be approximately equal to the cross product of those two derivatives multiplied by the delta u, delta v. Well, the cross product, because we don't have a k, we put 0 in the k holding place is going to be this determinant, which is going to be the determinant of my smaller matrix multiplied by my k, delta u, delta v, which is going to be my partial derivatives, these multiplied together, k, delta u, delta v. But since we have k, the magnitude of k is 1, then my delta A is approximately equal to these partials, so that determinant, delta U, delta V. And so we get our Jacobian of the C1 transformation is denoted as JUV and is defined by this 2 by 2 determinant. My Jacobian is the partial derivative of xy with respect to uv, partial derivative of x with respect to u, y to v, or y to u. Notice the top row is with respect to u, the bottom row is with respect to v, and I do the determinant, so I multiply these two, subtracting the multiplication of these two, which means my area approximately is going to be equal to the Jacobian, delta u, delta v, which is, and don't forget we have, just as a note, you do have to take the absolute value of the Jacobian. In 3 variables, we would have g, h, and k as our functions of u, v, and w. Also, it has h of u, v, and w. The Jacobian is a determinant of a 3 by 3 matrix where the first row is x, y, z with respect to u. The next row is x, y, z with respect to v. And the third row is x, y, z with respect to w. This also means that I have the derivative of x with respect to u, v, and w. Notice I have all my x's in the top row, u, v, w. All of my y's in the middle row, u, v, w. And all my z's in the bottom row, u, v, w. These are the same. You sometimes will see the Jacobian noted like this. So they're asking me to compute my Jacobian. That's all they're asking me to do at this point. They're not asking me to do anything with it. We're going to do something within a minute. So we know that this traditionally would be x is equal to 7r cosine theta. So in other words, x as a function of r theta is equal to 7r cosine theta. Y is equal to 4r sine theta. So in other words, y as a function of r theta is equal to 4r sine theta. Now to do my Jacobian, j of r theta, it is going to be my the determinant, the partial derivative of my x with respect to r first. So this will be 7 cosine of theta. And then my partial derivative of x with respect to theta, which gives me negative 7r sine theta. And then I'm going to do my partial derivative of y with respect to r. So this will be 4 sine theta. And then my partial derivative of 4 sine theta with respect to theta, which is going to be 4r cosine theta. Now I'm going to do the determinant. So it's 7 cosine theta multiplied by 4r cosine theta minus 4 sine theta. Let me do that in red. 4 sine theta multiplied by a negative 7, the sine of theta. So what we end up with when we get totally done is we're going to get 28r cosine squared theta plus 28r sine squared theta. And since we know that sine squared plus cosine squared is 1 all day long, my final answer is 28r. And we typically will find the absolute value of it. R, of course, is not going to be negative for us, so we don't have to worry about the absolute value, but we really should do that. Now, if I take a look at this one, I'm going to fill up my Jacobian with S, T, and U, which is going to be, I'm going to do the first row, which is going to be my X with respect to s, my x with respect to t, and my x with respect to u. So my first row will be 3, 4, and 1. Notice how those are the coefficients. And then our next one will be the y's. So it would be 3, -3, and -3. My last one would be my z's, which would be 4, -1, and -3. And that's because I can choose which order to put it in. I decided to do all of my with x's. So this is my x function of s, t, and u with respect to s, t, and u. And then I did my y function with respect to s, t, and u. And when I get done with this, doing my determinant of a 3 by 3, and we can either do this with a cofactor expansion or copy paste those columns and multiply up and multiply down and subtract appropriately, I end up with 120. Now, the whole reason that we learn all of this is to make our integration easier. Suppose our area is approximately equal to our Jacobian multiplied by delta u, delta v, where t is the transformation from s into r. So, and we're using by the definition of the double integral. So here's what's happening. We end up with this. So if I have some transformation from u into v, from the transformation uv into xy, where x is a function of u and v and y is a function of u and v, is 1-to-1, and it's a continuous partial derivatives transformation with a non-zero Jacobian on the interior of the region S. It maps S into the region R in the xy plane. If F is continuous on R, then we end up with this. We end up with this, which is most of the time much easier. 3 space, we end up with this. Just something to note, you always take the absolute value of your Jacobian. No matter what it is, you always take the absolute value. Now here's some strategies for changing your variable. Sketch the region by the given problem in the xy plane, and then write down the equations of the curves that form the boundary. Depending on the region or the integrand, choose the transformation where x is equal to guv and y is equal to huv. Determine the new limits of the integration in the uv plane. Find the Jacobian. The integrand, replace the variable so you obtain the new integrand, and replace dy dx or dx dy with the appropriate Jacobian du dv. So, we're asked to compute the area of the region bounded by x is equal to 1, xy is equal to 9, and xy squared is equal to 1, and xy squared is equal to 36. They are not giving me appropriate values to do replacements. So I'm going to have to figure out a good replacement. Now, a good replacement is I notice that I have the x and the y. So I have x times y in 2 places. I have x times y and x times y. So I'm going to let u equal x times y. Similarly, I see x squared and I see xy squared. So I'm going to have v equal xy squared. Now, we did this up above. If you remember, we already did these transformations. And what we had was, we had y of uv ends up becoming, my y was u over v. And I have my x, and we did this before, ends up being u squared over v. And this is the function. So u of x of uv, so excuse me, it's getting late and I'm getting tired. X of uv is going to be the u squared over v. Now, I got to figure out what my bounds are. So as I take a look at this, if u is equal to xy, then u is going to run between 1 and 9. 1 and 9. If v is xy squared, then v is going to run between 1 and 36. Now, it doesn't matter which one I integrate first, so one or the other. And I'm going to make that decision after I find my Jacobian. So I'm going to find my j of uv. So this is going to be, I'm going to do the derivative of u first, the derivative of x with respect to u, so it'd be 2uv. Then the derivative of x with respect to v is going to be negative u squared over v squared. Now I'm going to find the derivative of my y with respect to u first, which is 1 over v, and then minus u over v squared. All right, so I'm going to make sure I did that right. Derivative of u with respect to v first. Oh, I don't have my u, I don't have my y correct. My y should be v divided by u. So this is going to be negative v over u squared, and this one's going to be 1 over u. Helps if I have those in the right places. When I do this determinant, I get 1 over v. Since I have 1 over v, I'm going to integrate with respect to u first. I'm going to integrate with respect to v last, so v is going to go from 1 to 36. U is going to go from 1 to 9 of 1 over v du dv. When I get done, my final answer is going to be 8, the natural log of 36. And I can tell you what, this is a much nicer integration than if I would have tried to have done some kind of shenanigation with the finding who's the top and the bottom and the left and the right. Okay. Now I want to compute the region with the vertices of 0, 0, 2, 1, 4, negative 5, 2, negative, and 6. So the first thing I would have done is I would have graphed this thing, and it looks something like this. And I would have found the equation of this line happens to be y is equal to 1/2 x. And then I would have found the equation of this line, which ends up becoming y is equal to 1/2 x minus 7. And then I found the equations of these two lines. Now, what ends up happening is I end up with x minus 2y is equal to 0. That's what that line becomes. And this other line ends up becoming x minus 2y is equal to 7. Now, if you're thinking that would be a really good choice for you, then you would be correct. I would say let u equal x minus 2y. And then u would run between 0 and 7. Now, these other two lines right here, I end up with the line 3x plus y is equal to 0. That's this one. And then this line ends up becoming 3x plus y is equal to 7. So if you're thinking, let v equal 3x plus y, I would agree with you. So then my v would run between 0 and 7. So now I'm almost ready. I got to find my Jacobian. I also need to find my x's and y's in terms of the u's and v's. I ended up finding x is equal to u plus 2v divided by 7. And I end up having y is equal to negative 3u plus v divided by 7. Now I'm going to find my Jacobian. It'll be my derivative with respect of x with respect to u, which is going to be 1 over 7, and 2 over 7. I'm going to change colors on you. These should be in red. So 1 over 7 and 2 over 7. And then these would be negative 3 over 7 and 1 over 7, which ends up becoming 1 over 7 when I'm totally done. I skipped some steps. You're just going to have to work those out. Now, my integration that I want to do from x plus y of dy dx over this region is going to be, well, I'm going to integrate, it doesn't really matter. I'll do the 0 to 7 last. So I'll do my v last. So I'm going to integrate from 0 to 7 last. From 0 to 14 first. This is my u and this is my v. Now I have to replace my x with u plus 2v divided by 7 plus my v, or my y, which needs to be replaced with negative 3u plus v divided by 7 du dv. This is equal to, from 0 to 7, 0 to 14, and this ends up, I'm going to pull out, and don't forget I need to multiply by my Jacobian here. I got so excited I forgot to multiply by my Jacobian. So I need to have this 1/7 du dv. So I'm going to pull out this 1/7 out front, and I also see that I have, these are both similar to 7, so I'm going to pull another 1/7 out front. So I'm going to write this as 1 over 49. That's because this 1/7 and these can be wrote as 1/7 u plus 2v minus 3u plus v. And this ends up cleaning up to negative 2u plus 3. This ends up cleaning up to negative 2u plus 3v du dv. When I get totally done doing the integration and everything, I end up with a negative 7 as my final answer. All right, last one. Use a change of variables where s is, now they're giving me an appropriate s and appropriate t values. Find the area of the ellipse. So I need to solve for x. So x is going to be equal to, well, it's going to be s, actually I'm going to do a cursive s minus 2y, but y is equal to t, so x is equal to s minus 2t, and y is equal to t. All right, so let's do my Jacobian. My Jacobian of s comma t is going to be 1, negative 2, 0, 1, which ends up becoming 1. Now I need to convert x squared plus 4xy plus 5y squared into its appropriate s's and t's. So s minus 2t, the quantity squared, plus 4 s minus 2t multiplied by t, plus 5 multiplied by t squared, and this ends up becoming s squared plus t squared, which is less than or equal to 1. Oh, that's very lovely, actually. Very lovely. So my integration of my region from dx and dy is the integration of t ds dt, which ends up becoming the area of t, which is just going to be pi. So that's actually quite nice. Now we're going to revisit this lovely thing. Now, if you remember in 5.6 last week, this was a whole lot of not fun. It was a whole lot of not fun. So the first thing we're going to do is we're going to rewrite this as x squared divided by 1 divided by 3 squared plus y squared divided by 1 squared is equal to 1. That means x must be equal to 1/3 r cosine theta, and y is equal to r sine theta. My Jacobian of r theta will end up becoming 1/3 cosine theta, the sine of theta, and then negative 1/3 r sine theta, and then r cosine theta. Which, when I get totally done with all of this, is just going to give me 1/3 r. Nice. So now, my integration from 0 to pi divided by 2, 0 to 1, because that's my radius, is going to go from 0 to 1. My angle is going to go from 0 to pi divided by 2. So this is what we did all last week. Is going to be equal to the square root of 9 multiplied by my x replacement, which is 1/3 r cosine theta, plus sine theta squared. My 1/3 r dr d theta. Well, this cleans up quite nicely. This ends up becoming, and this is squared, this ends up becoming just 3 times 1, because I end up with, well, actually it just becomes 1, because I have 9 multiplied by 1/9, the cosine squared. Oh, forgot my r's in there. I just got so excited, I forgot my r's. So I have r, the sine of theta, the quantity squared. So this just becomes r. The square root of r squared, which is just r. So from 0 to pi over 2, from 0 to 1 of r squared, dr d theta. Don't forget the 1/3. I put 1/3 r, said 1/3 r, and I put 1/3 r. 1/3. That was my Jacobian, 1/3 r. So, nice, easy peasy, lemon squeezy, and we end up with 8 pi over 18. Holy smokes, this was so much easier than we did it last week. And this is why. Have you ever wondered why we got that r? Well, it's because of that Jacobian. So if I'm going from r theta into z into x, y, and z, the Jacobian is r. And if I have my function, and I'm integrating over this rectangular region D, or this region D, from x, y, z, dv, I need to have that r dr d theta dz for my Jacobian. That's where the r comes from. And for phi, theta, or rho, theta, and phi into x, y, z, my Jacobian ends up becoming rho squared sine phi. And so that's how come we have to have rho squared sine phi d rho d theta d phi, which is kind of cool. Last couple of examples here. We are going to look at the area of a region in different forms. The first form is You could totally find the area of this shaded region without knowing any calculus, as long as you know some knowledge with your pre-calculus. So the first thing we're going to do is we're going to take the x squared over, I'm going to divide everything, so I have the x squared, 4x squared plus 4y squared is equal to 1. I'm going to rewrite this as x squared plus y squared is equal to 1/4. So that tells me my radius on my inner circle, that's this one, is going to be 1/2. So I'm going to find the area of the sector for this, just that area. So I have to figure out what this angle is. They're telling me that this is x is equal to y the square root of 3. That means 1 divided by 3, the square root of 3 is y divided by x. That means if I take the tangent inverse of 1 divided by the square root of 3, then I end up with my angle, which is pi over 6. That's not what I want. I want this region. This region is pi over 3, because we know that pi over 3 plus pi over 6 is pi over 2. Which means the area of this small sector, I'll call it area sub 1, is going to be 1/2 my angle in radians, which is pi divided by 3 times my radius squared, which is 1/4. Then I'm going to find the area of this entire region. So to do that, I'm going to have x squared plus y squared is equal to 64 over 9. That tells me my r is equal to 8 over 3. A sub 2 is going to be 1/2 my angle, which is pi thirds, and my radius squared, which is 64 over 9. The area of the blue shaded region is going to be the area sub 2 minus my area sub 1, which ends up becoming, I have 32 pi over 27 minus pi over 24, which is approximately equal to 3.59247. Totally do that without knowing any calculus. Now I want to find the area of the region bounded by the curves in the xy plane. This is how we would have done it when we first learned double integration. I would have had to break this up into 2 pieces. So I have this region, and I would have had to break it up into 2 pieces. My first piece, I would have had to break up here, and I would have this first area. And I would have had to break it up into this area. So doing this first area, I ended up with 0. And this place on the x-axis ends up becoming the square root of 3 over 4. So the square root of 3 over 4. My y is bounded by those 2 circles. So it would be the square root of 1/4 minus x squared would be my lower bound. And then my upper bound would be 64 divided by 9 minus x squared, dy dx. That would just be my first region. And then I'd have to do my second region, which is this one right here. And it would go from 3 to the square root of 4 to this point. This point on the x-axis is 4 to the square root of 3 over 3. So 4 to the square root of 3 over 3. Now my x is going to bound between x, the square root of 3, x divided by the square root of 3, and my upper bound, which is that circle, 64 divided by 9, x squared, dy dx, and it would be a whole bunch of fun integration, and we end up with 3.59247. A lot more work. Didn't even have to do it by integration. Last one is I want to find the transformation t that takes my rectangular into an r theta plane. So in other words, I want to go into polar. So I have x comma y is going to be equal to the transformation of r comma theta, which we know the x value would be r cosine theta, r sine theta. And then we'd have x squared plus y squared is, so this is equal to 1/2 half the quantity squared. And we'd also have the other one, which is x squared plus y squared is equal to 8/3 squared. So we would have r on this side would be 1/2. And on this one, we'd have r is equal to 8/3. So now we found our bounds for r. Our theta, well, if we did look at our shape, we know our theta starts at pi/3, just like it did before, and ends at pi/2. So I could just start integrating, as long as, of course, that I have my Jacobian, which we know is going to be r. So I'm going to go from 1/2 to 8/3, from pi/6 to pi/2 of r d theta dr, and I still get 3.59247. So, which one's the easiest? Probably the last one, but you can totally do it without any calculus. The one that I would try to avoid is the one in the middle. And that's it for this section.